Hi, I'm Carlton Coffrin. In this video, I will be reviewing some core results from the technical report, The Potential of Quantum Annealing for Rapid Solution Structure Identification. This work begins with the D-Wave quantum computer, which is a sophisticated analog computing device that runs at near 0 Kelvin to perform an adiabatic quantum computation called quantum annealing. Through two high-profile publications in 2018, it became clear that this hardware could be used for certain types of quantum simulation, but in this work we'll be viewing it as a black box that performs discrete optimization problems. When you open the D-Wave user manual, you'll learn a very simple first-order approximation of what this hardware can do. It minimizes a model called the Ising model, which is pictured here in this slide. You have decision variables that are -1 and 1, and a quadratic function of those variables, and your goal is to find the minimal assignment of the variables, or the optimal solution. You may have also heard of quadratic unconstrained binary optimization, which is a similar structured problem except for the decision variables are 0 and 1. And these two are equivalent, so you can think of the hardware as solving either of them without any loss of generality. When I first encountered this interpretation of the D-Wave hardware, my response was, so what? These seem like particularly simple optimization problems, and it wasn't obvious to me how I could map real industry applications into these particular structures. Digging a little deeper, I discovered there were a variety of very challenging combinatorial problems which you can map into this type of model, like max-cut and max-independent set, and then I became very excited that maybe this hardware could transform the way we design optimization algorithms. And that begs a very obvious research agenda. Pick your favorite combinatorial optimization benchmark library, encode it as an Ising model, and then solve that Ising model on the D-Wave. This could potentially revolutionize the field of discrete optimization by bringing a new form of hardware into the mix for algorithm designers. So I pursued just this. As a first attempt, I took the DIMACS Max-Clique benchmark set, which includes a variety of challenging problems that have been tested over the years, and I designed an experiment where I solved them with a strawman solution and then tried to solve them on my D-Wave hardware. In this first attempt, I'm not going to go into a lot of the details because there's another video and talk which presents this in great detail. But at a high level, for small problems, I could show that the D-Wave hardware was producing high-quality solutions that matched the global optimum solution to this problem. But just as the tasks became difficult and very time-consuming, there were challenges in encoding these problems into the D-Wave hardware, and then we weren't able to get any information about how the hardware would perform on more challenging instances. This is not the first time this has happened, and it probably won't be the last, because there's a very inconvenient truth is that every attempt to show this type of an unquestionable D-Wave performance advantage on combinatorial optimization has failed. It's an active area of ongoing research. So the punchline of this particular technical report is a demonstration of a combinatorial optimization task where lanl's 2000Q D-Wave computer is 100 times faster than the best known classical algorithm. All of the results are available in this technical report on arXiv. Now with that said, I'll give three key clarifications. The first one is that we're not solving a real-world application. In this work, we solve a problem called a corrupted biased ferromagnet, which is a contrived problem that we developed to demonstrate some kind of a performance gain. This demonstration is only 10 to the 2 times faster, and I would not consider that an unquestionable performance advantage, but I would consider that a promising performance advantage. If we look at other quantum supremacy type of demonstrations in the literature, they're demonstrating things like 10 to the 6 to 10 to the 9 times faster, which is much more significant. That said, an improvement of 10 times faster over the state of the art is generally considered a significant progress by the optimization community, so these results are very promising in that context. Last but not least, I'm optimistic but cautious about this result. It is definitely possible that a clever insight on this CBFM problem could increase classical solver performance significantly and reduce the gap between the D-Wave-based algorithm and the classical-based algorithm. But we've tried our best to think of such insights, and we don't have any so far. So let me give you an overview of the talk. We'll begin by talking a bit of the benchmarking approach, which is primarily inspired by the optimization community's methods for benchmarking algorithms. Then we'll discuss some basic Ising model concepts, which help with the interpretation of the benchmark problems we're designing. Then we'll introduce the three core benchmark problems of this work, the biased ferromagnet, frustrated biased ferromagnet, and corrupted biased ferromagnet, and then conclude with some overall thoughts about the results. We'll begin with the benchmarking approach. The computational task at hand is to find optimal or near-optimal solutions to this particular Ising model optimization problem. It's NP-hard in general, so this presents a non-trivial computational task. Our goal is to claim that quantum annealing, or some kind of D-wave-based algorithm, is the fastest known solution approach for this type of problem. It is not trying to make a theoretical claim, this is a purely empirical claim based on experimentation. The primary challenge of this type of claim is the fastest known solution approach. There are lots and lots of solution approaches one could take, and enumerating all of them is infeasible. So in the optimization community, we typically focus on a small collection of approaches which are considered state-of-the-art, and then make incremental progress on those state-of-the-art approaches to improve the algorithms overall. This work considers 7 solution methods, 3 of which I would consider state-of-the-art alternatives for benchmarking, and then 4 of them are more like straw men to give some intuition for how different approaches might work and provide breadth, because we don't want that some particular algorithm class could have very high performance and we just miss it. One side question we're trying to answer with this work is what type of algorithmic features does quantum annealing bring that other algorithms do not? This really requires a deeper analysis than we go into in this work, but I believe this provides a nice foundation for starting to ask that type of question. So let's talk about the different algorithms that we're considering. The first category are complete search algorithms. These algorithms provide global optimality proofs, so if you run them long enough, you'll get a certificate that you have the correct solution to the problem. We consider 2 options, integer quadratic programming and integer linear programming, both of which are implemented by a commercial software called Gurobi. I would consider integer quadratic programming state-of-the-art for some classes of problems that are being used for benchmarking D-wave. In terms of local search, we have a variety of heuristics. We have Glauber dynamics, which is a type of MCMC heuristic. We have min-sum, which is a type of belief propagation or message passing algorithm. And then we have a steepest coordinate descent algorithm, which is a type of greedy algorithm. Our primary contender is an algorithm called HFS, which is a large neighborhood search approach and is widely considered a state-of-the-art solver for benchmarking the D-wave. And last but not least, we're going to test quantum annealing via lanl's D-wave 2000Q computer. One common question I get is what about things like simulated annealing, quantum Monte Carlo, spin vector Monte Carlo, and then parallelization on GPUs? To answer that question, I would refer to this technical report, which did an extensive study of all of those methods and the contents of benchmarking optimization algorithms, not simulating quantum physics, which are very different questions. And the conclusion of that report is that HFS is a very strong heuristic and sets a very high bar for performance gains. So if you can beat HFS, you're very likely to be beating these other methods as well on the current D-wave architecture. In terms of experimental data and what problems we'll be solving, we're going to focus on D-wave native problems. So we're going to take the D-wave hardware graph, which has a very particular structure, as pictured on the right-hand side of this slide. We're going to put that into a problem generation algorithm, and then we're going to output a particular optimization task, which can be natively represented on the D-wave hardware. We can then feed that problem back into the D-wave for solving, and then into all these other algorithms for comparison. Because we have a problem generation tool, we're going to generate hundreds of random cases and present mean values over an ensemble so that we're not biased to one particular instance of those cases. In terms of classical algorithms, we're going to give them one thread, and we're going to measure a wall clock time limit ranging from 0.01 seconds to 1,000 seconds, so that's 6 orders of magnitude, and we're going to return the best solution that can be found in that given amount of time. For quantum annealing, we're trying to keep it simple. There's a lot of features on the D-Wave platform we could use, but we just try to keep the experiment as simple as possible in the interest of replication. So we emulate different runtimes by setting the annealing time to 5 microseconds, and then setting the number of reads we'll take on the D-Wave between 10 and 10,000. As we take more reads, it takes more time, and so this simulates different types of time limits. We'll always return the best solution among all the reads that were executed. In terms of D-Wave runtime, we're going to be reporting total real time as returned by the D-Wave server, which measures the amount of time that was spent in the quantum processing unit on the chip. Specifically, this excludes communication and scheduling time, which is approximately 1 to 2 seconds. But it's reasonable to assume with significant engineering efforts you could eliminate most of the communication and scheduling time. We're going to use as a metric a thing called a performance profile. So what we're going to have on the x-axis is runtime in a log scale, and on the y-axis the solution quality or solution energy. So all of the algorithms will have a curve that looks like this, which shows you the best solution that's been found for the given amount of elapsed time. We're also going to have a flat line which represents the best possible energy or the optimal solution. And typically we're going to measure a relative gap to this optimal solution, which is called the optimality gap. This is convenient because for different problems with different energy scales, it normalizes them all to a consistent metric. One of the things that I like about this metric is that with better engineering, say code optimization, we can shift this curve to the left. We can make things converge faster, but we can't shift it down. The asymptotic trend is remaining the same. So this gives us some insight if better engineering would change the game, or if there's a more fundamental algorithmic problem to work out. Let's begin by demonstrating the methodology with a random field problem, which is well established from the literature. So in this case, the problem generator just sets the quadratic and linear terms to -1 and 1 uniformly at random. In a 2017 report, we proposed that this was the most interesting case for benchmarking in the literature. So let's look at what the performance profile metric for the 7 algorithms we're discussing looks like on this particular problem. So there's the performance profile. And the first thing you can see is that this looks like a challenging problem. The good news is that all of the classical algorithms except for HFS have a significant optimality gap, and it's taking a lot of time for them to decrease. And so for some of these algorithms, like the MC-MC algorithm or the steepest gradient descent algorithm, we can see that even if we engineered it to be 1 or 2 orders of magnitude faster, it wouldn't actually change the ranking of algorithms here. So there's a really big algorithmic challenge that needs to be conquered to improve these particular algorithms on this instance. The good news here is that quantum annealing, which is represented in green, is doing very similar to HFS, which is represented in orange, which is the state-of-the-art heuristic that we're trying to beat. This suggests that quantum annealing is comparable to the best local search approach that has been designed for this particular problem. Let's zoom in and just look at the results right here, because right now they look kind of on top of each other. It's hard to distinguish them. So when you zoom in here, you see a more nuanced picture where at very, very short timescales, maybe the quantum annealing has an advantage, but very quickly the HFS algorithm is outperforming it. So that's unfortunate, but one of the core criticisms we've made in our previous work is that this energy scale is very small, less than 0.5%, which for practical purposes would mean that these solutions are indistinguishable. So although this plot may look like there's a big difference between HFS and D-Wave, for practical purposes that may not be the case. They may just be equally good at solving this problem. This motivates the need for a better benchmark. So another message from this 2017 report was that none of the benchmarks we have for quantum annealing were sufficiently challenging for all of the classical methods considered, and especially HFS. And we conjectured that if we can build a more challenging problem class, and it was suitable for the D-Wave hardware requirements, then quantum annealing and D-Wave would outperform the alternatives. So in this work, we propose a problem design approach. We're going to start with a problem that D-Wave is very good at solving, which is called a ferromagnet, and then we're going to make tweaks to that problem until it's hard for all the other classical solvers considered. So before we can start introducing that, let's give a brief crash course in basic Ising model concepts. So an Ising model is this quadratic function we've introduced before. Let's consider a very simple example with just two decision variables, or two spins. Here we're going to represent each spin as a graph. So you have a node for each spin like this, and then for the quadratic terms we're going to draw edges in the graph. To represent the coefficients in front of each one of these terms, we use a color scale which goes from dark blue to red. And then we can encode these coefficients of -1 and 1 using these colors. So throughout the rest of the talk, you're going to see pictures of our D-Wave hardware graph colored with red and blue, and this is just a graphical representation of whatever this Ising model energy function means. First thing is that links have special names called ferromagnetic and anti-ferromagnetic. In this case, a negative link is called ferromagnetic because intuitively it encourages two spins to take the same value. So if you consider this simple one-edge two-spin model, the optimal solution is -1 and -1, or 1 and 1, when the coefficient is -1, so it's a ferromagnetic link. Positive links are called anti-ferromagnetic because they have the opposite property, which encourages spins to take opposite values. So in this case, the optimal solutions are 1 and -1, and -1 and 1. The next big concept in Ising models is the idea of frustration. And the basic property here is that not all of the local preferences can be satisfied at the minimum energy solution, or the optimal solution. So in this example, you have frustration because there's a triangle where two of the edges want all the spins to take the same value, and one of the edges wants to be different. So there's no way to make all of those satisfied at the same time. One of the edges cannot be satisfied. Here's an example of a different model that has no frustration. All the spins want to take the same value, and one of the spins prefers the up position, and everyone can be satisfied in this example. You don't need frustration to occur in the edges, however. So a tweak on that example is that everyone wants to take the same value. Some of the spins prefer to be up and some prefer to be down. And in this case, you can still have some frustration where not all of the properties can be satisfied. This is an important concept because frustration is required for an Ising optimization problem to be computationally challenging. If you don't have frustration, simple greedy algorithms will result in optimal solutions. The last core concept is the idea of a gauge transformation. And this is a symmetry group of Ising models where you can flip the signs of the spins but keep all the other properties the same. So if you recall, this is the no frustration example from the last slide. We can swap, say, the lower right-hand spin to be the opposite sign and change nothing about the problem as long as we change the edges as well. So this is a very interesting property because when you see an instance like this one, where you see a lot of different colors and there doesn't appear to be any structure to it, it may actually be a very simple problem because a gauge transformation could have been used to obfuscate all of the structure that would otherwise be visually obvious. So with that basic foundation of Ising models, we can start to talk about the three different types of problems that we developed in this work: the biased ferromagnet, frustrated biased ferromagnet, and corrupted biased ferromagnet. We begin with the biased ferromagnet, which is the simplest problem. In this problem, we're going to set all the edges to -1, so the whole hardware graph wants to take the same value. And then for a few spins, roughly 1 in 100, we're going to give a preference for a particular direction, which is down. Then this will give a small bias to one particular side. If you look at the zoomed in picture in the lower portion of this slide, you'll see that there's one spin with a light blue coloring in it. And if you look very carefully at the large graph, you may see that there's a number of those which are giving a bias to a particular side. So it's fairly obvious to see that this has an optimal solution where all the spins are set to 1 and there's no frustration. So you can satisfy all of the coefficients which are in this problem. Now in practice, we're going to apply a gauge transformation to this instance to hide the problem structure from the different algorithms and mitigate hardware bias issues in the specific D-Wave device. If we think about this from an energy landscape point of view, it has a fairly intuitive function that's easy to understand. So in this plot, we're seeing all of the possible assignments of the decision variables from all 1s to all -1s, and then we have the energy there, and our goal is to minimize the energy. So if you have a standard ferromagnet with no bias in it, you have 2 deep wells at the extreme points of this picture, where everything is 1 and everything is -1. So these have the exact same energy. What we've done by putting a few rare biases on some of the spins is that we've made one of these wells slightly higher than the other. In expectation, it's 0.01 times the number of spins in the system. And the reason we've done this is that if we start some kind of a local search algorithm, it can get stuck in this very deep well, which is the wrong side, and then it can have a lot of difficulty escaping this very deep well. And our hope is that using quantum annealing and superposition and quantum mechanics, that it can see through these 2 very distant wells and select the right one. So here is the performance profile for the biased ferromagnet instance. And you can see that almost all of the lines are very low on the graph. They're all on top of each other, which makes it hard to distinguish. So these are very easy problems, which is maybe not surprising because there's no frustration in this model. A good algorithm should be able to find the optimal solution here because you can do it easily with a greedy algorithm. An interesting side result here is that this MCMC global dynamics algorithm gets stuck around 15% away from the optimal solution. So there is some local minima structure in this particular problem, even though it's not a super difficult problem in general. Let's zoom in to this part of the graph to understand in a little bit more detail what's going on. And what you can see here is that the vast majority of instances our algorithms are finding the optimal solution. The energy scale here is more interesting, so it's about 1%. That's good news. And a surprising result is that this very performant HFS heuristic in some number of cases gets stuck indefinitely in the wrong well. And so even though with certain types of structure this algorithm is very good, this gives a structure where it can get stuck. So given that insight, we're going to work on building a better benchmark. So this one has the core properties that we want in that quantum annealing is very good at solving this problem, but it's too easy for all those other algorithms. 6 of the 7 approaches can easily find optimal or near optimal solutions to this problem. So the next idea is to add some frustration to the biased ferromagnet to make the problem more challenging. So we propose this frustrated biased ferromagnet, which has the same structure, except in some cases we're going to set a local field to -1, and with a lower probability we're going to set it to 1. So if you look at the zoomed in picture in the lower right part of this slide, some of the circles are colored red and some are colored blue, and there's going to be many more blue ones, about twice as many blue ones as red ones. So this will still have an optimal solution, that's the same as before, but it'll have a small amount of frustration based on the local fields. And most importantly, there has to be some kind of a long-range consensus across the whole hardware graph to determine which of these 2 wells is the correct one or the lowest energy one. And here again we're going to apply a random gauge transformation, and this has a valuable property in that it hides which of these h values is the best one. So if you were just to look at this problem without the gauge transformations, you could just count the number of h's in one direction and the other direction, and then you could easily pick the right side. But that's not so obvious to do once you have applied the gauge transformation. So interestingly, the energy landscape picture is the exact same here, because in expectation the well is still off by 0.01 times n. And we still have the same issues where local search can get stuck in one of the wells and not the other one. And we hope that quantum annealing will do better. So if we look at the profile here, the good news is that this is a much more interesting case. So 3 of the 7 algorithms we were considering moved much higher off of the optimal solution. So we have things like 5 or 10% gaps in the beginning and then going down steadily. If we zoom in on the real competitors for this problem, we see an equally good story. So we still have that this problem is hard for some runs of the HFS algorithm, but the bad news is that for the relaxation complete search methods, this is still very easy. So essentially these integer quadratic programming and integer linear programming methods see through the structure of this instance and instantly find the globally optimal solution. So it's not kind of an intrinsically difficult problem. So here we can try a third take on building a better benchmark. So this frustrated biased ferromagnet is challenging for many of the local search heuristics, but it's too easy for these relaxation-based methods. We need to make modifications to the quadratic terms of the problem, because frustration in the linear terms is clearly not enough. We draw ideas from the spin glass and doped ferromagnet literature, recalling that RAN F case that we showed in the beginning of this talk was very challenging for all of the methods considered. Maybe some of the idea of corruption or doping could make this particular problem harder. So the core idea here is to add a careful amount of corruption to this biased ferromagnet instance to make the problem hard for these relaxation-based methods, but also not to lose the structure we've seen before with the 2 wells. So this is the final instance we propose, called the corrupted biased ferromagnet. Here we take the biased ferromagnet and then we add as well a change in the J's. So now there's a 0.62 probability that they are ferromagnetic and a 0.375 probability that they're a weaker anti-ferromagnetic. So the light red lines indicate the anti-ferromagnetic links, and the group blue ones are the ferromagnetic links. And then the H's stay the same as they were in the previous 2 cases. Now we had to tune these parameters, both the probability and the strength of the J's, very carefully so that we still have these 2 deep wells. And then again, we're going to apply a random gauge transformation so that it's harder for some of the algorithms to see this structure. So if this was the BFM landscape from before, now we have something more like this, where we still have the 2 deep wells, but there's a lot of small valleys in between that one can get stuck in. So if we look at the performance profile for this particular instance, it's a similar story as before, but the good news is that both of the relaxation-based methods now have increased significantly in the gap they have. They ultimately do prove the optimal solution, but much, much slower than the other heuristic algorithms. So this instance continues to be challenging for HFS, which is the state-of-the-art heuristic, so that's also promising. Meanwhile, the quantum annealing performance remains consistently good. One thing that is quite surprising about quantum annealing is in all of these cases we've sent it, its performance is more or less unchanged. So it seems to be pretty flexible in terms of the types of problems it will happily solve. Let's zoom into this particular region, which is the most interesting, of course. So here is the zoomed in version of that. And this is really a great success in that quantum annealing is clearly the fastest algorithm at these shorter timescales. And if you choose to run the quantum annealing for only a very few number of runs, you still have a very significant performance gain over HFS, and here we can see the optimality gap is around 2.5%, which would be considered in industry practice to be significant, much more significant than 0.5%, which was the case for that RAN instance. And then if you want to hit a particular quality target, you're going to get a big runtime advantage as well. So either way, it's a good news. And in the beginning of the talk, I promised 100x performance increase. So here is 100x in this log scale of runtime. And you can see if we pick a particularly low optimality gap, we have that 100x performance increase. One question that comes up often is what's going on in this region where things are kind of converging towards 0? And one way we can look at that is by making the y-axis a log scale as well. So now we have a log-log scale, and again I've repeated the 100x measure, and you can see for different optimality gaps you actually have a very similar performance gain. So that's also very good news because it kind of means whichever quality of result you want, you still get a very significant performance gain. So that's the core insight of this or core contribution of this particular technical report. We also asked a couple of other follow-up questions. The first one is this really a novel insight, or do other benchmarks out there have a similar property? Other benchmarks have not used the same metrics as we have, so it's useful to repeat the same analysis with those cases. So 3 of the most popular instance classes are this RAN-F1 case, which we talked about at the beginning of the talk. That goes back to 2013. There was a weak-strong cluster network case proposed in 2016, and then also a frustrated cluster loop with gadgets case. I think it's important to note that these last 2 cases were designed to show features of quantum annealing and not really to benchmark the system against state-of-the-art alternatives. So the goals here are quite a bit different, but they're still interesting cases to test nonetheless. So if we take the weak-strong cluster network case, the energy scale is smaller, so 6% is pretty small for all the problems that we've considered here. But the good news is that many of the heuristics don't find the optimal solution. When you zoom in here, HFS is clearly beating over the quantum annealing approach. And most importantly, these relaxation-based methods are finding the optimal solution. You have to do a lot of tuning on this instance to find cases where that isn't the case. But in any case, this energy scale is very small, less than 0.1%. So in practice, there's probably not a big difference between these instances. So there might be useful insights to be had here, but they're not for practical optimization purposes. When we look at the frustrated cluster loops with gadgets, the story is a little bit more interesting. So there is a huge optimality gap for some of the approaches. And the instance is non-trivial for some of the complete search approaches. So if we zoom in the interesting region again, there is a significant performance gain here of approximately 100%. So this is somewhat similar to the result that we have for the corrupted biased ferromagnet. But the results seem to be somewhat of a middle ground between the frustrated biased ferromagnet and the corrupted biased ferromagnet. They aren't as dramatic as the corrupted biased ferromagnet. One disadvantage here is that the global search solutions can find the optimal solution in approximately 1 second, say 1 to 5 seconds, which is very fast. In practice, that's pretty great. And also the energy scale here is only about 1%, where with the corrupted biased ferromagnet it's about 2.5%. So overall I would say this is also a very positive result for benchmarking, but you can have even more dramatic results by using something like the corrupted biased ferromagnet. So going back to the value of a better benchmark, now that we have an instance class that shows a significant performance gain, we can start to do new and interesting things like hybrid solution approaches. So this is really just a proof of concept to show that this is possible, But there's a fundamental problem with all of the heuristic algorithms we've considered, which is that you don't know when to stop. With these types of algorithms, you run them for a certain amount of time, and then you just hope that you find a high-quality solution, but you don't really know. And this includes using the quantum annealing approach because it's some kind of a stochastic analog device, and it gives you a lot of different solutions, and you're not quite sure if it's found the best one. The core benefit of these complete search algorithms is that they finish eventually. They're exponential time algorithms, but they have a very clear stopping criterion, and they provide an optimality proof at the end. And so for many practical instances, they can converge and produce a proof and stop quickly. And so the CBFM results suggest that we could have the best of both worlds by developing a hybrid algorithm where you first collect some samples from the D-Wave hardware. In this case, we're going to do 1,000 samples, which takes approximately 0.2 seconds. And then we take that solution and we feed it in as an initial starting point for the complete search methods so that they don't have to find a high-quality solution on their own. So when you zoom in and you look at the performance of CBFM on this particular case, we now have a new algorithm, which is like purple or dark red, called hybrid, which first runs the D-Wave, get a good solution, and then feeds it into the IQP algorithm to further improve that. And what you can see here is that it always has a fantastic solution, even at the 1 second timeout. And then after some time, approximately 50 seconds, it has proven that that solution is the global optimum solution, maybe made a slight improvement to it, and then it can terminate. Where if you look at the orange line with HFS, you never know if you've searched long enough, and so you have to set a timer for a particular threshold and just hope. So definitely it's possible to design these hybrid algorithms and have the best features of both platforms. So with that, I'll move on to some concluding remarks. There are some things in the technical report that I skipped over. One of those is the proposal of solution Hamming distance as an interesting metric. We think this is a very valuable metric because it highlights the quantum annealing performance. It's less sensitive to energy scalings and small errors in the solution, which are common in an analog setting. And that's really where the idea of fast solution structure detection comes from. We observe very similar plots to the runtime plots, but in terms of Hamming distance. So you could use quantum annealing to kind of find a reasonable initial assignment to your problem that then you can polish with classical solver after the fact. We also have some initial results on the types of distributions that quantum annealing is sampling from and why it seems to perform so well on the CBFM instance. And we also have an appendix which includes a uniform field variant of all three problem classes. These are generally easier problems for all the algorithms, but they have very similar trends. And in some cases, the quantum annealing performance gains are even more dramatic than what we presented here, but we selected these three cases as the primary ones because they seem to be the most challenging for all possible algorithms that we tested. So some final thoughts. It does appear that quantum annealing can deliver near-optimal solutions very quickly compared to other classical approaches. It requires the right conditions. The problem needs to be very difficult. The coefficients need to be scaled and in a convenient way that works well for the hardware. And its ability to identify these near-optimal solutions does seem to be unique amongst these local search approaches, so that's very exciting. It may be bringing something new that current optimization theory does not bring for us. The biggest gains occur at very short timescales, so that is a new insight for me, which is after maybe 10 to 100 runs of the hardware, you've gotten most of the information you're going to get about the optimization problem. So that suggests that online or feedback algorithms would be effective because you're only going to run the hardware for a very short amount of time. And that also implies that communication, scheduling, chip programming, all of those overheads will be very critical in practice because we're only going to do very, very small jobs on the hardware before submitting another one. So with that, thank you very much for sticking until the end of the talk. Various resources will be in the video comments. And if you have any questions, please feel free to reach out to us. We'd love to hear from you.